Part of the functionality that is being developed in Sedimentics project has to do with integration of the instrument with the hospital information systems. For this to happen, we developed software components that reside both in the instrument side and on the HIS side, and manage the communication between these two entities and the exchange of HL7 messages that support the exchange of information related to demographics, laboratory orders, and order results. This functionality will be demonstrated in the Maribor Hospital, and at this phase of the project we have delivered the final prototypes of the software components. We are now running the beta testing of the communication infrastructure, and we will soon install the software in the HIS in Maribor Hospital in order to execute the trials.
The CDMedics instrument is used for two different chips. One that is performing a serological analysis, antibody detection, and one that is performing genetic analysis. Both chips fit into the same slot, and the machine can adjust its execution to each of the slots automatically. Both chips have the same footprint.
Hello, my name is George Kritikos, I'm from Microgen, and I'll demonstrate you the chip definition software, which is needed to annotate flows and alarm points on the chip so that the camera will know where to look for the flow movement. Here we'll annotate this meandric flow, like this, so the user will know the total volume of the flow, and we can also add some alarm points for demonstration. And the software is also capable of performing volume measurements from point to point in flow, like this. So that's about the basic functionality of the software. It can also save and load from XML files so that every annotation made is not lost. And we can also add annotation to already made from other user or another instance of the software, for example.
Hello, my name is Anastasios Moraitis and I work for Microgen. I'm an electronic engineer and I'm going to demonstrate today the flexibility of the instrument we have fabricated here in Microgen, and it is used primarily for the CDMedics project, where we can we target to detect the coeliac disease by examining the blood of a patient, but also an instrument that can be used for trying different types of experiments and figuring out more than one diseases or biological tests, or running more than one biological tests. What I have next to me is the software companion for that helps us in that process. The first screen you can see is where we show the instrument which chip we are planning to use. We can use different chips that have different uses. So I'm just going to, for demonstration reasons, just going to take one for HLA. You can see it's defined here. Then an experienced user can do whatever he or she wants with this simple drag and drop editor. On one side we have all the components inside the machine. You can see that there are some valves, two-way, three-way valves, some LEDs for lighting, as simple as that, or more complex components like mixers, magnetic mixers, or stepper controls, like the pump, the syringe pump we are using, and virtual components that help with the structure of your basic experiment and the analysis of the analysis and the process you want to do, like the loop, switches, alarms. The basic idea behind this instrument is that it can handle any component of any type, and as easy as drag and drop it inside this editor. A very simple example, just for demonstration reasons. We have a phase, subphase, and a sequence. This is the primary structure. I will just drag and drop one LED. I will set it off, or all the LEDs, so that this can be visible, right and left. So I just set it off here. After 5 seconds, I will light them back on. As you can see, I just drag a sequence, I put it under a subphase. I could as easily drag a subphase, put it under the phase. I could as easily have a different phase. So if you have something more complex and you want structure in it, it is very easy to have it. Like for example, a DNA amplification procedure. It's a more complex example. I will show you later one. It's quite big. So we'll just now turn them back on again. All the commands available are here. It's very important to say that the machine is so flexible that any component can have any type of commands. For example, a LED can be checked if it is a most simple component. You cannot just light it on or off. You can check if it is on. You can check in its position. You can check its status, and referring to its status, you can do another action, and so on. So I have my simple assay ready, and I just download it to the instrument. It's ready already. And now I will go to the instrument. As you can see, this is a 2D representation of the 3D image I have, so I can see my chip here. Another way to see it is to use the camera. Maybe we will see this later. And now I will just press play, and you will be able to see here that the lights will go off, and after 5 seconds will turn on again. They turned off and on. Very simple. Not all assays are as simple as that. The trained personnel can do more complicated assays. One of these is the assay I'm going to show now. Yeah, it takes some time to load. As you can see, it is one very big assay. What this do is a complete analysis for the CDmedics the CDmedics project, the Qualec disease. It introduces the sample, it prepares the blood sample, then it makes PCR amplification, and at the end sends the sample to the electrochemical sensors to measure the result. These 4 phases show this, and every phase can be as simple as sample introduction or as complicated as PCR amplification. You can see here. I will demonstrate now how easily the different components can be added on the instrument. So, any component you want to use, and by component I mean any actuator. It can be a simple one or a group of components, like a stepper motor control, a LED, a valve cluster, a complicated thermo controller card. Practically any actuator that has to do with microfluidics and analysis is supported by this instrument. So what you just do, you plug your hardware on the machine. It has plenty positions. So back to the hardware configuration. Again, I will demonstrate that you can reach for a component like a stepper control, and just drag and drop it inside the hardware configuration area, and then you just connect to any component to the component that it's supposed to fit here. No? Let's select the channel that is not in use. And that's it. I drag it somewhere so that you can see it. I can change the name and beautiful stuff as that, but I can change its functionality. This is the most important. So I have a set of commands that are associated with this specific component, and I can add more. As many commands as I like. Whatever the component can do, it can be described in the hardware configuration file. Even if you update your hardware, you can still describe it here. It is it's an abstract layer that gives us a great functionality and flexibility. So I will just remove it now because I will not be able to run my experiments. Yes. Great. Other functionalities associated with the software companion for our instrument are as simple as help and options for the communications, and more important, like firmware update for updating the firmware on the machine, something like updating your cell phone's software. What we are running here is an initialization for the PCR amplification protocol. We put our sample in the PCR part of our HLA microfluidic chip, and then we are ready to run the assay for that particular part of the process. So I just press play as before, and what it does is it moves the sample from one side, the cold side of the chip, to the hot side of the chip. The temperature here is about 60 to 62 degrees, and here 90 to 98. This is the range. The actual temperature is very accurate. In this particular example, we have 60 and 90. So as you see, the sample goes back and forward in order to achieve polymerase chain reaction and amplify the DNA. When it is in the cold zone, the sample we put it to wait for 20 seconds before it moves to the hot zone again, as you can see it doing now. The whole procedure lasts 40 cycles, and at the end we have an amplified DNA sample. What you can see here is the image taken directly from the instrument with the use of the camera control. The camera, it is used as any other component. We used exactly the same procedure we described before. We just plugged it in, we set some alarms. It's just another component. More complex, of course, but just another component. Because the lamps are not quite visible, I will show you. The first alarm is here. Oh, you see, I don't know if you could see a rectangle blinking when we reached the alarm, and the second one is here. You will see when we will reach it. As you can see, the camera software detects the liquid at both sides, at both ends. It waits again at the cold zone, and then it will move back to the hot zone.
My name is Thanos Damiris. I'm with Micro2Gen, and I'm the work package leader for instrumentation in the CD Medics project. I'm going to say a few words about our first instrument prototype here, which was designed having flexibility and adaptability in mind. While in the development cycle of a research project, it's necessary to frequently make adaptations. And for the instrumentation, usually this is a huge problem. because you have to redesign the interfaces to the microfluidic chip. You have to change your electronics, you have to adapt your software. So within CityMedics we went another way and designed flexible software that is capable of handling all these modifications in an easy way. There is a software application that is used to configure different types of hardware and different types of protocols, assay protocols to be executed in an easy and user-friendly way. In addition, we try to introduce some novelties in this instrument, one of which you can see right behind me. We eliminated all light barriers that are usually necessary in instruments of this type to control the flow of the fluids. Instead, we use a low-cost camera, which is monitoring the flow of the control, of the flow of the fluids at all times, and can detect it passing through given spots, and then give signals to the rest of the hardware to react correspondingly. What you can see here is an oscillating PCR. This is a 2 temperature zones PCR, which is basically moving the fluids back and forth, thus achieving the temperature changes that are necessary and in many different cycles, and in as many cycles as you want. This was introduced by a partner in the project, IMM, and you see here an implementation where the control of this oscillating PCR takes place with the help of the camera. 2 alarm points are positioned at the ends of this meandric structure, and every time the fluid reaches one of these ends, the control stops the motion, the fluidic motion, and returns the fluids back. You have here a low temperature zone, approximately 60 degrees, and you have a high temperature zone, 90 to 95 degrees. The CityMedics instrument is heading for the point-of-care market. Its main goal is to make this type of analysis accessible to the medical doctor. That's why it's designed to have a relatively compact format, and it's in a second iteration, in a second prototype, it's going to be even more compact. In order to be able to support both medical end users and research the same, the instrument is accompanied by 2 different distinct software applications. One of them being giving the means to the medical end user to insert a chip and perform an assay and get a report back, and the other one giving access to all details of the implementation and being able to control all aspects of the instrument. One major innovation of this instrument is basically using one slot for different types of chips. You can use the same slot for a micro device to perform antibody detection, and you can use the very same slot with a different protocol to perform genetic testing. The instrument prototype is a joint effort. It was the mechanical design was performed by Micro2Gene, along with the software to operate it. The electronics were designed and implemented by Clemens and Micro2Gene, and all the fluidic aspects, actuation aspects, were designed by IMM and Microfluidic Chipshop, and all the aspects related to biosensors and readout of biosensors by University of Tarragona and the University of Newcastle.